Isaac Newton's laws of motion and universal law of gravitation are foundational principles in physics that describe how objects move and interact with forces. Newton synthesized these laws into a cohesive framework in his landmark work, Philosophiae Naturalis Principia Mathematica, 1687, revolutionizing our understanding of the physical universe. Here's an overview of these laws and their significance. Newton's three laws of motion. First law of motion. Law of inertia statement. An object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. Explanation. This law essentially describes inertia, the tendency of objects to resist changes in their motion. If no external force acts on an object, it will either remain at rest, if initially at rest, or continue moving in a straight line at constant speed, if already moving. Significance. This law refuted the ancient notion, from Aristotle, that continuous force was needed to keep an object in motion. Newton showed that motion persists naturally unless interfered with by forces like friction or other resistive factors. Second law of motion. Law of acceleration statement. The acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to its mass. Mathematically, it is written as F equals ma, where F is the force, m is the mass of the object, is the acceleration. Explanation. This law quantifies how much an object will accelerate when subjected to a force. The greater the force applied to an object, the greater its acceleration. However, the larger the object's mass, the less it will accelerate for the same applied force. Significance. The second law provides a quantitative relationship between force, mass, and acceleration, enabling precise calculations of how objects move under various forces. Third law of motion, action-reaction law statement. For every action, there is an equal and opposite reaction. Explanation. This means that when one object applies a force on a second object, the second object simultaneously exerts an equal and opposite force on the first. Forces always come in pairs. One object pushes or pulls on another, and that object pushes or pulls back. Example, if you push against a wall, the wall pushes back with an equal force, even though the wall doesn't move. Significance. This law explains how motion occurs in many contexts, from rockets launching into space, propellant gases push backward and the rocket moves forward, to the simple act of walking, your foot pushes on the ground and the ground pushes you forward. Newton's universal law of gravitation statement. Every mass attracts every other mass in the universe, with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Mathematical form. F equals G asterisk M asterisk M2 slash R superscript 2, where F is the gravitational force between two masses, G is the gravitational constant, 6.674 times 10 superscript 1 superscript 1, and M superscript 2 slash Kg superscript 2. M and M2 are the masses of the two objects. R is the distance between the centers of the two masses. Explanation. Newton's law of gravitation states that every object in the universe exerts a gravitational pull on every other object. The strength of this force is proportional to the product of their masses, meaning more massive objects exert stronger gravitational forces. However, the force diminishes rapidly with increasing distance, specifically with the square of the distance between them. For example, if the distance between two objects doubles, the gravitational force between them becomes 4 times weaker. Significance. Explains planetary motion. Newton's law of gravitation explained the orbits of planets around the Sun, refining Johannes Kepler's earlier laws of planetary motion. Newton showed that the same force of gravity that causes objects to fall on Earth also governs the motion of the planets.